The reactions of the amines that we're going to look at are rather limited. Some of them you've seen already. First of all, acylation, that's just changing an amine to an amide. Alkylation is where an amine will do SN2 on an alkyl halide. We've seen elimination before where an alcohol or an alkyl halide will eliminate to form an alkene. Well, amines can do the same thing. It's a little bit different how they do it, but we're going to look into that. And we've looked at electrophilic substitution of aromatic amines. We're going to review that, plus we're going to look at some ways to handle amines so that we can do some reactions that normally we don't cover in aromatic reactions because amines need a little special treatment. And then last of all, we're going to look at something called the Sandmeyer reaction, where we take an amine and derivatize it to a diazonium salt, and then we can do some substitutions. Acylation is an old reaction for you. An acyl halide with an amine gives you an amide. Alkylation is also an old reaction for you. An amine can do an SN2 on an alkyl halide. Now, it does need to be primary in order to have substitution predominate. If you have secondary or tertiary, you would start having elimination occur as the major reaction. But even a primary alkyl halide, we don't really use this for alkylation per se, because we get a mixture of mono, di, tri, and quaternary substituted nitrogens. And that's not a real great situation. Now, one exception is if we want to get the quaternary ammonium salt, all we have to do is use an excess, and it will take us all the way to this quaternary ammonium salt, and there'd be no mixture. Quaternary ammonium salts have 4 alkyl groups on them, and a positive charge on the nitrogen, and then you have a counter ion. We call them quaternary ammonium salts or tetraalkyl ammonium salts. They are both water soluble and organic soluble. The alkyl groups make it organic soluble, and the salt portion makes it water soluble. And we often will use them as transfer reagents to take a water-soluble anion and pull it up into an organic solvent that normally it would not go into, but as a counter ion to the quaternary ammonium salt, it will. And we'll look at that later on. A quaternary ammonium salt that's important in biology is acetylcholine. There are many other examples, but you can see 4 alkyl groups on the nitrogen and a positive charge, and there's your counter ion. Always remember that if you have 4 bonds on a nitrogen, it has a positive charge, and then you have to have a counter ion with it. Quaternary ammonium salts act as an excellent leaving group, and they will eliminate to form alkenes. This is very much like alcohol dehydration, except what we will see is that you get the less substituted alkene. You cannot do it with a regular amine. You have to have a quaternary ammonium salt. If you have a nitrogen that is let's say a tertiary amine, no elimination will occur if you treat it with a base, because the leaving group is going to be way too basic. But if we alkylate it until you get a positive charge on the nitrogen, then what happens, and then treat it with a base, you have elimination occur quite easily, because that nitrogen with its positive charge now is a good leaving group. This is called the Hoffman elimination. Here's an example. Here's this amine, and what we do is we alkylate it until we get the quaternary ammonium salt right here. Then we treat it with a base. Here it's a silver oxide, and that's typically used because it's a real gentle base, but other bases will work. what does this base do? It removes a proton from the less hindered carbon. This is very, very bulky, and so the base won't want to come in here and remove the proton from here. It comes into the less hindered side. So in contrast to alcohol or alkyl halide elimination, in which you form the more substituted alkene, with a Hofmann elimination, you get the less substituted alkene. Here's an example. Here's the amine. We treat it with excess methyl iodide, and it gives us the quaternary ammonium salt. Then we treat that with silver oxide, the base, and the proton, not here, but here, is removed, and we get the less substituted alkene. Okay, here's a picture of the transition state in the elimination. Silver oxide actually reacts with the water and makes silver hydroxide, and then that hydroxide removes a proton. And notice you have anti-elimination occurring because it is just an E2 reaction. The difference from the other E2 reactions is this hydrogen is on the less substituted carbon. Here's an example of which hydrogen will be removed. Again, more substituted, less substituted, less hindered. This is where the proton is removed to give you the less substituted alkene. So if we want to get the more substituted alkene, what do we use? We use a dehydrating agent with an alcohol and see what we get. We get the more substituted alkene here with phosphorus oxychloride. If you had an alkyl halide, you could just treat with sodium hydroxide. Here we have an amine. If we treat it with an alkylating agent and then with silver oxide as our base, notice we get the less substituted alkene. So now here are a bunch of reactions for you to try. Go ahead and determine the outcome of these reactions. In this first reaction, we have an acid halide and an amine. What does it form? An amide. In the second reaction, if we treat this amine with excess methyl bromide, we end up getting the alkyl ammonium salt. This alkyl ammonium salt, now treated with silver oxide, we will get elimination. So elimination will occur right here. And we get this alkene. Here's another one. If we treat this with methyl bromide, again we would get the quaternary ammonium salt. Elimination, though, remember, has to give you the less substituted alkene. And I put this in here just so you would look and think about the outcome of this reaction always giving you the less substituted alkene. When you have aromatic amines, you can have electrophilic substitution. The amine is the strongest activator that we have, and it's an orthopara director. However, it's incompatible with Friedel-Crafts acylation or alkylation. The reason it's incompatible with alkylation is that the nitrogen will do SN2 on the alkyl halides that are necessary for the Friedel-Crafts reaction, and you end up making the quaternary ammonium salt, and the positive charge on that nitrogen deactivates the ring for any electrophilic substitution. Acylation, it will not occur because acylation conditions will acylate the amine and cause the amide to form. So keep in mind that an amine is a very strong activating agent, and it's so strong that when we go to brominate, we don't even need aluminum bromide to act as a catalyst to help the electrophilic substitution. Bromine, just like with phenol, bromine adds directly to the ring, and it keeps adding because it's so activated. Let's look at electrophilic substitution now. We know that amines are very strong activators, ortho-para directors. If we acylate the amine and turn it into an amide, it is still an ortho-para director, but because the non-bonding pair is tied up in the pi system, it is less of an activator. Because it's an activator, Friedel-Crafts, acylation, and alkylation can go. The only thing that's nice about this is you can acylate the amine group that protects it. And then you can remove the acylation by using acid or base, and you return it to an amine. So basically, what we're talking about is covering the amine group with an acyl group, doing an electrophilic substitution, and then removing that so that you get your amine back. But these are words, and they're confusing. What we need are pictures, right? So let's go ahead and look at that. Okay, this aniline cannot undergo a Friedel-Crafts alkylation like this right here. Why? Because this will alkylate this nitrogen repeatedly until it makes a quaternary ammonium salt. That's going to be deactivated then. That positive charge will make it so that electrophilic aromatic substitution cannot occur on the ring. So what do? We acylate it. Now, alkylation will not occur on that nitrogen because a non-bonding pair is tied up here and it can't do an SN2. However, the ring is still activated, and this is still an ortho-para director, and we can take this alkyl group and add it to the ring with Friedel-Crafts condition, and then use sodium hydroxide to cleave off this acyl group. And we get this net effect is that we get what we want. But you have to remember, multiple alkylations can occur. If we want, what we can do is acylate the amine, get our amide down here, and then we can use Friedel-Crafts acylation, and we can then get ortho or para substitution of the acyl group. Now, cleaving it, we get the amine back, and if we want to, we can reduce this down to an alkyl group if we want. That's not a problem. So we can do both of these reactions with that amine in place by acylation first.